afternoon, everyone. Welcome to Taco Tuesday, commercial style. This is Brett Zerba, application/training engineer with Taco. And before I turn it over to Rich, I want to tell you what I just told him. I turned 65 on Saturday the 23rd. The
Isn't
same
there a
day,
song about 65, Brett? Oh, no, it's 64.
the same day, I have the same birthday as Gino Ariema. Some of you may know who he is. He's the UConn women's basketball coach. He turned 70 though. Anyways, welcome to Taco Tuesday, and we're glad you're here. Couple, as usual, can a couple people raise your hands so you know you can hear us and see us? Please, couple. Anybody? Uh-oh. Okay, woo. Thank you. Somebody did.
Oh,
Okay, I got some now. All right. Hallelujah. Hallelujah. Hello. We got some people typing in some hello. Hello from Kansas. David's is in Kansas. I hope the weather's better there. Did you get any snow, David? I don't know if you were in that crazy range out there where they were getting snow. So today's topic is introduction to NPSH. I'm not going to tell you what that stands for. Hopefully some of you already know. No snow, David said. No, that's good. Parts of New England, upstate, got almost 3 feet of snow on Saturday. It poured like the Dickens here near the coast. But anyways, NPSH, a topic that is, a lot of times it's overlooked in HVAC hydronic systems, and we all need to understand it and be aware of it. And Rich Medeiros, who will be talking shortly, loves to advertise. Do the calculations. Think about it, please, because he has some examples he will discuss of some big issues on that. So 24 hours from today, you'll get a link to the video or the recording. This is being recorded, and access to your PDH certificate. Also, there's a handout available. Hopefully, you might be able to see that on your screen. You can download it. It is the PDF of today's presentation, so you have access to that if you want to look back on it as you go on. Oh, someone's from Vermont. That poor person. I bet you they got some snow. Anyways, let's see. Taco. 104-year-old company. No, 104 years old.
104.
My God, we
Just think if we added my age to your age, we'd be over 100.
Yeah. Neither of us, neither Rich nor I, as old as we are, were around when Taco first started. I do want to go on for that.
Hey, you know who was around that period of time though? In 1903 is when the Wright brothers first flew their plane.
Wow.
Wow.
I think Taco had something to do with that. No, maybe not. Maybe not.
Did you think they used a pump impeller for the propeller on the plane?
Yeah, they might have. They might have. But probably not. Probably not.
Probably not.
Thomas says hi from Maine, so he may be seeing some white stuff out his window as well. So, anyways, many of you have been on these presentations before. Please ask questions. This topic here does lend itself to some questions. Some may be relatively simple to answer. Some may be a little more in depth. We will try to get to them all as we can. I will be monitoring the questions as we go. And my very good friend, Rich Medeiros. Rich and I spent some time together recently. Where the heck were we, Rich? We were in Biloxi, Mississippi.
That was really nice.
That was
I mean, they happen to have a cold spell for them, but for us, it was beautiful.
And we were in 2 hours east of that in Pensacola. That's right, Pensacola, Florida. Yep. So, anyways, I guess I'm talking and done talking, introducing. I think I mentioned everything already. Like I said, I'll be monitoring the questions. My very good friend Rich will be doing the presentation. And at this point in time, drum roll, please. I am going to turn it over to Rich. Rich, take it away.
Well, Brett, thanks for that great introduction. Good morning, or actually it's noontime, so good afternoon, everyone. At least noontime here on the East Coast. of the United States.
All
So
right.
today's topic,
I need to interrupt, Rich. Allie is saying there's no voice. Can a couple people type in and say you guys are hearing us? And maybe it's just with Allie's system. We hear you. Okay. We got a lot of audio that's saying we hear you. Okay. Apologize, Allie. I'm not sure what's going on with your computer, but I've got 10, 12, 15 people saying we can hear you, which is very unusual. Take it away,
it is.
Rich.
So today's topic, we like to call it Introduction to NPSH. So what are we going to cover today? So with a little luck, I'm going to try pressing a couple of buttons, and of course the buttons don't work. Why does that happen, Brett? Every time I press these silly little buttons, they don't seem to work. All right, let's try it one more time. Here we go. All right, there it is.
Hallelujah.
Whoa. Okay, what is NPSH? Properties of water. We'll talk a little bit about water. How to find net positive suction head NPSHR, which stands for required. We'll get into all of these in a little more detail in a few seconds here. How to calculate NPSHA, which stands for available. We'll talk about the difference between those two. And then we'll have some questions. So what is NPSH? I like to put the formal definition up here. And since this is a webinar broadcast, and you can download, what is it, 24 hours from now, Brett? They can download this presentation,
Yep.
which means that you can capture this definition where it says that NPSH stands for net positive suction head. And this is the formal definition. Net positive suction head, or NPSH for pumps, can be defined as the difference between the liquid pressure at pump suction and liquid vapor pressure, expressed in terms of the height of the liquid column. And since we're talking about water today, we will be talking about that column of water relative to water. Okay. And the abbreviation NPSHR stands for net positive suction head required by the pump. And the only place you can get that information is from the manufacturer. It's not something you can calculate on your own. You have to get it from the manufacturer. And then the other term is the net positive suction head, NPSHA, which is the net positive suction head available from the system. And that's something that you would calculate. And we're going to actually do both today. We're going to find the NPSH by the manufacturer, and we're going to do a little sample problem. So let's see what else have we got here. I like to start off with a container of water, and I'm going to switch. Brett, hopefully you can still hear me out there. I'm going to switch to my whiteboard here, and with a little luck, can you see my whiteboard?
I can.
I'll just put a little happy face over here just to make sure that everybody out there in computer world, webinar world, can see my. Can you see that happy face?
I can.
Okay, great. So let's get rid of that. And let's draw a little container. So let's draw a container here. Now for today's discussion, our container is going to be partially filled with a liquid called water. Let me try putting that on here. Look at that.
I think you spelt it wrong. It's Wadder.
You think it's water?
Water.
And let's say that it's open at the top. And we have to make a couple of assumptions. We are at, for today's discussion, we are at sea level. Whoops, this is supposed to be an elevator. We are at sea level. And let's assume that our container is open at the top and the temperature of the water is 100 degrees Fahrenheit. Now, just to make sure they're all on the same page, let me just move this to the side just a second here, because there's one thing I do want to define. Because in the pump world, we typically measure pressure in feet of water column. So I'm going to draw a column of water over here. This is just an open pipe. Let's make it like, again, it's open to the atmosphere at the top, and we are at sea level. And let's just pretend that we have an elevation of water from the bottom of the tank to the column or pipe. That height, let's just make that 2.31 feet. And to make the column, to make the units proper, it would be feet of water column, WC, and in this case, G for gauge pressure. Now, if I have a column of water that's 2.31 feet tall, and I put a conventional pressure gauge that reads in pounds per square inch at the very bottom of the column, that pressure gauge is going to read 1 pound per square inch gauge pressure. So therefore, the conversion between a column of water and pounds per square inch is 2.31. So I'm going to give you a very simple example. If I have 10 pounds per square inch gauge pressure, and I multiply that by 2.31, that's feet per PSIG, then that will come out to 23.1 feet. So that's the conversion between pounds per square inch and feet of water column. So with that in mind, hopefully, well, because we're going to record, we are recording this. Hopefully we are recording this, right, Brett?
Yep.
And that means that I don't really have to leave it on the screen for any length of time, because you can always go back and look at the recording. So I'm going to erase most of this stuff here, and then we'll get back to our tank. But it's important to realize that that conversion, and in the pump world, we measure pressure in feet of water column as opposed to pounds per square inch. Actually, we measure it out in both cases, in both units, but we want to make sure that we distinguish between the two. Okay, so I'm back to my container. It's at sea level here. Make sure I underline it. Whoops, there's my sea level. There's sea level. Now, I can get this water to boil. Let's see if some folks will type in, Brett, when I ask this question. Tell me if they get this right. If I add some heat, I can get this water to boil at sea level. If I raise the temperature of the water inside the container up to some other temperature, and I'm going to put in just a question mark here, degrees. Whoops, that was silly, wasn't it? It's kind of a silly line there that I just created. All right, so in other words, I'm going to have some temperature in degrees Fahrenheit. And does anybody want to type in and tell me what temperature would I have to increase that water to in order to get it to boil at sea level? Has anybody wrote that in there, Brett?
I see some people writing in 212 degrees.
That's a good number. That's a good number. 212 degrees Fahrenheit. Now let's repeat over here that we are at sea level. And it turns out that at sea level, the atmospheric pressure, we can say that 1 atmosphere, 1 ATM. By the way, some people remember ATM as atmosphere. Don't get it confused with automatic teller machine, where you cash your checks. I guess you don't cash checks. You just go to the machine, you put your card in, and it spits out cash. That's good. And so 1 atmosphere is equal to 14, approximately, not exactly, 14.7 pounds per square inch absolute pressure. And then if I wanted to convert that into feet of water column absolute, I would multiply that by 2.31, and hopefully someone can do that arithmetic. And I can say that 1 atmosphere, just converting it to units, is equal to approximately 33.9 feet. I'm going to repeat the units, feet of water column, and in this case, absolute pressure. All right, but in the pump world, we typically don't actually write the units water column and absolute or gauge or whatever. We just write feet, and we're supposed to know whether it is gauge pressure or absolute pressure or differential pressure, those kinds of things. We'll get into that in a minute. So that's the conversion. Now, I can get this water to boil without adding any heat. So I'm going to erase here for a moment. I'm going to erase this temperature. I'm going to get rid of the heat. Look at that. That's pretty cool. But now I'm going to close off this container. I'm going to put a top on the container so it's no longer open to the atmosphere. And let's pretend that it's a 100% sealed container. And then I'm going to put in on the right over here my vacuum pump. There's my vacuum pump. And I'm going to evacuate the air that's in this container. And it turns out that I can get this water to boil at 100 degrees Fahrenheit if I can reduce the pressure. So let me put a pressure gauge over here. It's a little pressure gauge. on the side over here. And I'm going to reduce the pressure to a very low pressure until the pressure gets to approximately 0.94924 pounds per square inch absolute. And that water will begin to boil. Look at that water boiling there, Brett.
I like it.
I like it. It's got nice little bubbles. If I multiply that value, by the way, by 2.31, that's the conversion, then my value will come out to approximately, not exactly, but approximately 2.2 feet of water column absolute pressure. So let me repeat. I can get this water to boil at 100 degrees Fahrenheit by reducing the pressure, put a magic vacuum pump in there, until my pressure gets to 0.94924 pounds per square inch absolute. If I multiply that by 2.31 feet per pound, PSI, sorry, pounds per square inch, it comes out to approximately 2.2. So if I have 2.2 feet of water column absolute pressure in my container, that water will begin to boil at 100 degrees Fahrenheit. So do we have any questions out there, Brett, before we go on to the next piece of the puzzle here?
It's not that appropriate of a question, but I'm going to ask it anyways. Steve said, "What's a check?"
What's
when
that?
you mentioned getting a check in the mail or whatever, someone wants to know what a check is. He's probably never seen one in his life.
Oh yeah. Oh yeah. We used to use those.
I actually, in one of my classes, I'm pretty sure it was high school, it could have been before that, we actually had a class or part of a class where we learned how to write checks.
Yeah, I mean, before computers came along, that's how people got paid. And
I,
there's
I
this
don't even
whole
want I don't even want to mention. I mean, I actually used to balance my checkbook,
yeah, I
and it,
don't do
it
that.
came out. No, I stopped doing that, but I'm still aware of whether I have money or not. Anyways, that's the only question we have, my friend.
Now I'm frightfully geflupped. I have no idea where I left off. All right, let's move our container off to the left a little bit. I'm just moving it off to the side because now I want to make a little sketch. I want to make a sketch of the cross section of a pump impeller. So here's what a pump impeller might look like if I cut it and I look at a section of the pump impeller. All right, so here's the inlet over here, inlet. I'll just point to that. There's the inlet. And let's just make some dotted lines here that represent the vanes of the impeller. This isn't the greatest drawing in the world, but you get the general idea. So the water is going to flow. So let's pick a different color for the water. Let's pick blue. I like blue today. And then the water is going to flow through the impeller from the inlet to the outlet. And by the way, the impeller inlet is also called the eye of the impeller, eye, E-Y-E. All right. So it turns out, let's make the water temperature at the eye of the impeller 100 degrees Fahrenheit. And let's pretend that the pressure at the eye of the impeller is 2.2 feet of water column absolute pressure. And if that's the case, guess what's going to happen to that water at the eye of the impeller? It's going to start boiling, just like my bubbles in my little container over there. All right, that water is actually boiling. Now, since the water is boiling, the water is also flowing through the impeller. So as soon as the pressure increases, and certainly at the inlet is the low pressure, so I'm going to label that low pressure. And then at the outlet of the vane, that's highest pressure. Highest, EST, pressure. So somewhere in that transition between lowest pressure and highest pressure, those bubbles are going to collapse. And when those bubbles collapse, they implode and they create shock waves. And there's millions of tiny little shock waves which can eat away at the impeller. And I'm going to show you a picture of what that eating away of the impeller looks like in a few minutes. So those bubbles that collapse, that phenomenon of collapsing bubbles is called cavitation when it comes to a pump.
Hey, Rich.
Yes.
So I want to bring this up right now. So Steve is asking, is this for 0% air in solution?
This particular example, we're not talking about air. We're talking about water changing phase from liquid to a gas or liquid to steam. And we're not talking about air in this phenomenon, just what happens to the water. We're going to assume that for now, that the air stays in solution, it doesn't come out, and it doesn't affect this little example. Does that help?
Yep.
Okay, do we have any other questions out there that someone's dying to ask?
Nope.
All right, so what we want to do is we want to make sure, in order to keep a pump impeller from cavitating, we want to make sure that the inlet pressure is high enough so that the water does not boil at the inlet. That means in our particular example, we have to make sure that the inlet pressure at the eye of the impeller is greater than 2.2 feet of water column absolute, because if it's equal to that or less, the water will boil. Now, I'm going to do something else here. I'm going to kind of encase my weird looking little impeller. Let me move this down just a little bit here. Kind of shrink it down just a hair. And I'm going to draw a impeller, a pump casing. Now, this is not a scientific casing. This is more diagrammatic. So you get a general idea of what's going on here. So I'm going to have a flange out here. This is my flange for my pump. That's on the suction side of the pump. So that's suction. There's my suction. Okay, and then I'm going to create this really bizarre looking impeller. It has another flange at the outlet here, and then it kind of encases the whole pump. And so here's the suction side of the pump, and here's the discharge side of the pump. So I'll label that discharge. Look at that, discharge. Now, this is a gross drawing, but what we want to make a point of is that there is a pressure drop that takes place between the suction. I'm going to put a pressure gauge here. There's a pressure drop that happens at the suction flange, between the suction flange and the eye of the impeller. Again, the eye is the entrance to the impeller. And let's assume that that pressure drop from the suction to the eye of the impeller, I'm kind of just doing a gross thing here. Let's say that that delta P is equal to 26 feet. That means that whatever the pressure is on the suction side of the impeller, the pressure is going to drop 26 feet at a given flow, and we're going to look at that in a minute. And that potentially, if the pressure at the inlet or the suction of the pump is 26 plus 2.2, then that would be 28.2 feet. In other words, I would have to have a suction pressure of 28.2 feet. If that was my value and the pressure drop was 26, I would have 2.2 feet at the eye of the impeller, and so that would start cavitating. So I want to make sure that my pressure at the inlet is always greater than, in this particular example, based on my temperature, and which I haven't talked yet about the flow, but I will talk about that in a minute. It has to be greater than 28.2 feet or it'll cavitate. And so by definition, the net positive suction head required by the pump in this case is approximately 26 feet. Because if it's any lower than that, by the time the pressure drop takes place, based on the water temperature, we'll have a problem and it will cavitate. So that's called the net positive suction head required by the pump. And it is actually the pressure drop between the suction flange of the pump to the eye of the impeller. Well, that was exciting. Okay.
Yes, it was.
So let's go back now to our PowerPoint presentation. And let's see if we can get this little guy to work. Yeah, that works. Okay. So where
Yep,
did
we're
we
there.
actually get the, go ahead, Brett. I'm sorry.
Nope, we're there. We're back.
We're back. So where did we actually get that pressure? Well, it turns out that you can Google it, and you can Google, you can type in steam tables and inch-pound units. That's what I had. I Googled it and I came up with this properties of saturated steam, sometimes referred to as the steam tables. And on the steam tables, the first two columns always tells us there's the temperature and the absolute pressure. It tells us what the vapor pressure, or the pressure at which the water will boil at a given temperature. So in our example here, I said, well, what is the boiling point pressure at 100 degrees Fahrenheit? So there's 100 degrees Fahrenheit, and look at that value, 0.94924 pounds per square inch absolute. So I didn't make up that number. I looked it up in the steam tables, and that's how I came up with it. And to convert it into feet, you multiply that 0.94924 pounds per square inch absolute times 2.31. I'm going to do it here live. 2.31 times 0.94924. The actual value comes out to 2.1927, and I rounded it off to 2.2. So that's where I came up with that value. So as long as you know the temperature of your water, you can look up in the steam tables what that's actually going to be in terms of the pressure. And that's called the vapor pressure. The vapor pressure, by definition, is the pressure at which the water will boil at a given temperature. All right. So just to make sure we know what we're talking about here, let me just go back here 1 second. I want to, let me just discard this. Hold on 1 second. I have a table here, which I'm going to share with everyone. Here it is here, NPSH. And this is the complete steam tables that I downloaded from the internet. It's called Table of Saturated Steam. This is what the actual steam table looks like. So there it is. There's the unit, the name, Saturated Steam Tables. I found this online. And again, I'm going to blow it up so everybody can see it okay. And as I scroll down, you can see at that 100 degrees Fahrenheit, the water will boil at 0.94924. But look what happens when I go to the next page here. By the way, if you notice, the temperature is like 100, 105, 110, and so on. Then on the next page, it continues that 155, 160. And then look at this one number right here, 200, 205, 210. And then they put this number right there. And that is the boiling point of water at atmospheric pressure. So if atmospheric pressure is 14.696 pounds per square inch absolute, the water will boil at 212 degrees Fahrenheit. So that's where we came up with that number from before. Isn't that exciting, Brett?
Yes, we have another question.
Yes.
So the NPSH is different for fluid temperatures, hot water versus chilled water?
No, the NPSH is always the same regardless of temperature. It's when you do the net positive suction head available calculation that you introduce the temperature of the fluid. The NPSH is simply the NPSH required by the pump is the pressure drop from the flange to the eye of the impeller.
10-4.
Okay, so I showed you a moment ago the steam tables and where I got those values. Now with a little luck, I'm just going to go over to this little diagram here. So, let me skip this diagram because I want to come back here in a minute. How do you find net positive suction head required by the pump? Well, it turns out that the, while I'm chatting in the background here, let me just grab one of my triangles from my drawer here.
Rich is coming back.
He's coming back.
He's coming back. He's on his way.
All right, I'm going to put a ruler here on this, and hopefully my little pen will still work. Let's see if it does. So at 2,400 gallons per minute, my little pump selection here, and let's say this pump's running at roughly 2,400 gallons per minute at 125 feet. If I continue that vertical line, and I'm just going to make it dotted now, until I get right up here where it intersects this value right here. See this curve? It says required net positive suction head. And that is where you get the net positive suction head required by the pump. You get it from the pump manufacturer. And in our case, we have a nice little graph that gives you the units on the left side in feet of water column. So see, it's just above the 25 feet, so that's approximately 26 feet. So I'm going to write that over here, 26 feet. As the flow increases, let's say it goes from 2,400 gallons per minute up to 3,000 gallons per minute. If I drew a vertical line at the 3,000 gallons per minute mark, you can see that the value kind of takes off here. Let's see if I can do this without messing this up here. And draw it all the way up here until it intersects. And so I'd have to extend that curve up a little bit. You can see it would be over, look at these units, it'd be 50, 55, 60, 65, is that units? 25, 30, 35, 40, 45, yeah, 50, 55, 60, 65, 70. It's about 75 feet, way out here, it's 75 feet. So it's a function of the flow of the fluid, in this case water, through the pump. So the net positive suction head required by the pump is, again, the pressure drop between the flange of the pump and the eye of the impeller. And the greater the flow, the greater the pressure drop. So hopefully that makes sense to everyone that's listening to us right now.
Question came up. How do pump manufacturers produce that curve?
It's a great question. Let me go back to my whiteboard here in a second. I want to discard all that for a moment. Okay, so let's go back to my whiteboard. I'll move this over to the side here. So the way we do this is, let's assume that this is our pump. I have a little pump. Oh, I don't like that color. Let me go back to red here. I like red. Let me erase this for a minute. There we go. Now I'll go back to red. Okay, so let's assume that I have a pump, and the pump is physically, got a little, and I'm going to make a flange over here on the suction side of the pump and another flange over here on the discharge side. You kind of bear with me here. This is kind of a gross sketch of what a pump should look like, but you get the general idea. So here's the suction, I'll label that S, and here's the discharge, I'll label that D. And let's assume that a pipe is connected to both the suction side and the discharge side over here. And then I'm going to put a valve, a manual valve on the suction side, and I'm going to put a manual valve on the discharge side. All right.
Do not take a picture of this and use this in your MEP drawings. No manual valves on the suction side, or be careful.
Well, you can have a valve as
you
long
can
as
have
it's
them, but don't use them.
It's got to be open.
Don't use them.
Yeah, don't do that, as Arnold Schwarzenegger would say. So don't do that. Okay, so let's go back here and just make sure that I wrote down the right number. I think it was 2,400. Yeah, 2,400 gallons per minute at 125 feet. So let me go back to my drawing. So this pump is pumping 2,400 gallons per minute at 125 feet. Whoops. I kind of screwed that up. Whoops. What I really want was the eraser here. Try this one more time. Let me move this up a little bit so that it's a little easier to see. Okay, I'm going to put a pressure gauge. Whoops. I have to remember, I have to shut off my eraser. So I'm going to put a pressure gauge on the suction side of the pump. And that's got some kind of reading. And then I got another pressure gauge on the discharge side. Actually, what I want to do here is, let me erase these pressure gauges, because what I really want is the pressure gauges to be mounted on the flange of the pump. No, I did it again, Brett. Let me see if yeah, there we go. Okay. So let's put a pressure gauge here, and that's going to read some very low pressure here. And then we're going to have another pressure gauge over here, and that's going to read a higher pressure. All right. So this is on the suction side, and this is on the discharge side. Suction side is here, discharge side is here. So in our example, I think we had 2,400 GPM, and I believe I had that at 125 feet. I'm going to check this in 1 second here. Let's just go back quickly and check to make sure. 125 feet. That's my design operating point. And at that point, my pump, my NPSH for this particular pump, my NPSH required, that's an R down there, is equal to 26 feet. And then, so I'm trying to answer the question, how do we figure that out? Well, according to the Hydraulic Institute, if we're measuring a pressure differential, let's say our delta P is 125, right? I can maintain that pressure differential, but what I'm going to do is I'm going to start closing down on the suction valve here, and I'm going to look at the pressure differential. I may have to adjust my discharge valve in order to maintain a constant pressure. There's a point at which the pressure differential, I can no longer maintain that 125 pounds. And when that pressure differential degrades by 3%, so in this case, 125 times 0.03, which is 3%, if that delta P changes by 3.75 PSI, then we say that the pump is cavitating. When I say we, the Hydraulic Institute says the pump is cavitating because we can no longer maintain that pressure differential. So by closing the suction valve until the pressure differential can no longer be maintained by as much as 3%, then we say the pump is cavitating, and that's in accordance with the Hydraulic Institute standards. That's a little mouthful, isn't it?
Yep. But that answers the question.
That answered the question. And hopefully give that a little thought, because we're going to go back to the presentation here and go on to the next piece of the puzzle. So how do we find the NPSH required? We simply look on the pump curve, because every manufacturer will publish that data. We at TACO put this nice little graph in there so that you can see, the graph is at the top here, and you can actually see, in this case, the net positive suction head required by the pump, in which case it's just above 25, and I'm calling 26 feet over here. And that's where you get the value. That's what I meant very early in the discussion. The only place that you can get the net positive suction head required by the pump is from the pump manufacturer, because we have to do that test in order to record the data. You can't calculate it. You can estimate it through calculations, and our pump design team does that, but until you actually put it in a test stand, you don't know exactly what the required net positive suction head required by the pump is. Okay.
Andrew has a great question here.
Sure.
So the pump, so kind of follow this. So the pump head in feet decreases and the NPSH in feet increases as flow increases. Is that true for all types of pumps?
Well, I can speak for centrifugal pumps because that's our area of expertise. I can't speak for other pumps that are, for example, positive displacement pumps, gear pumps, piston pumps. Those are all other pumps. I can tell you what centrifugal pumps, because that's our area of expertise, because that's the only type of pump that we manufacture and test.
Excellent.
Okay. All right, so here's a little diagram, because now we're interested in how do we calculate net positive suction head. So over here on the left side, repeating the definition here, I'm just going to kind of point to the first one. The net positive suction head required by the pump, that's from the pump manufacturer. We've already established that. And in our case, we said that needs to be approximately 26 feet. But the net positive suction head over here, available from the system, we have to calculate that. And we always want to make sure that the available pressure is greater than the required pressure. So we have to use this equation over here in order to figure out what the pressure is available. So we're going to calculate the net positive suction head available. And it's got 5 terms in it. The first one is the atmospheric pressure. The second one is the vertical distance between the center line of the pump and the water level. And in this case, it's an open system. It's open to the atmosphere. And I'm going to tell you what that looks like in a few seconds here. We also have to calculate the friction value. We have to calculate the velocity head and the vapor pressure. So the vapor pressure is a function of the temperature. So we simply look that value up. So I'm going to erase all of these wonderful little things here and go through this one more time. So the atmospheric pressure becomes a function in our little system here, is a function of the elevation above sea level. And since today's discussion is at sea level, then that's fixed. We can't change that. And the other thing is that we said our water temperature inside our system is 100 degrees Fahrenheit. And we have a cooling tower over here. And that cooling tower is an open cell cooling tower. It means it's open to the atmosphere. So that means that the pressure that's pushing down in all directions at that sea level is approximately 14.7 pounds per square inch absolute, or 33.9 feet of water column absolute. So what I like to point out, I'm going to repeat this because it's people get a little confused sometimes, is that the atmospheric pressure, which is the first term in this equation, and the vapor pressure, those are fixed. The vapor pressure is fixed because we have a fixed temperature in this case. And the atmospheric pressure is fixed because we're at sea level. I'm sorry, the atmospheric pressure is always fixed as a function of elevation above sea level. And since we are at sea level, those two terms are fixed. So the only ones we have control over is the vertical distance. I'm going to erase this and just emphasize those little guys right there. Sorry about that. Is these three terms: the vertical distance, the friction, that's the pressure drop, and the velocity pressure. Those are the only three terms that we can manipulate. So what do I mean by the vertical distance? Well, the water level inside the cooling tower is at this elevation. So I'm going to draw a line here, a little arrow. And the center line of the pump is way down here. And that elevation difference is, in our example, is 2 feet. So when we talk about the vertical distance, we're talking about the water level that's open to the atmosphere and the center line of the pump. Whenever the pump is below the water level in the open container, which in this case is an open cell cooling tower, that's a positive value. And if you notice, this term has a positive and negative value. If you move the pump above the water level inside the cooling tower, that becomes a negative value. But we don't ever want to recommend that you put the pump above the water level in an open system. It creates a whole series of problems that we have to solve. But we're going to erase this, and I'm just going to highlight this. So this vertical distance winds up being plus 2 feet. All right. What's the friction? Well, the friction is a calculation like any pressure drop calculation. We have probably some kind of fitting over here as it enters the cooling tower. Then we have a straight run of pipe. We've got an elbow, more straight run of pipe, another elbow. We have an isolation valve. We have some kind of strainer. There could be a variety of other components in the system. And we're going to say that that pressure drop, if we calculated it out, and we're just going to guess and say that's approximately 20 feet of pressure drop, 20 feet. So our delta P as a function of friction with all of the fittings and the pipe and the valves and the strainers and all that stuff is approximately 20 feet. All right. So now I'm going to start plugging in the values in a moment here. So let me erase this stuff. And I'm going to go to the next slide. And I have put in some of the values here. So in my case, the atmospheric pressure, since we're at sea level, we said is 33.9 feet. We said that the pump is below the center line of the pump is below the water level in the open cell cooling tower by 2 feet. So that's where the second term comes from. There's the 2 feet. And we said we calculated the pressure drop in the piping system, which included the pipe, the fittings, the valves, the strainer, whatever's in that system. And that came out to 20 feet. I'm going to, and then the last value is a function of the vapor pressure. And in this case, it's 2.2 feet. And we got that from the steam table. So the only one we haven't defined yet is how do we calculate this value, which is called the velocity head. Well, it turns out that the velocity head is equal to the velocity squared divided by 2 times the gravitational constant. So if I substitute values in there using the inch-pounds unit, I would say my velocity head is equal to, let's just going to make up a velocity of 8 feet per second. So I'm going to put in feet per second. And then we're going to square that whole term and divide it by 2 times the gravitational constant, which is 32.2 feet per second squared. Isn't that cute, Brett?
I love your math. Simple.
It's just a wonderful thing.
Yes.
So I'm going to rewrite this. I'm going to say, I'll write it over here to the left a little bit. Oops, didn't mean to do that. I'm going to say that the velocity head is equal to, now I'm going to do the arithmetic. 8 squared is 64. And then feet squared is feet squared in seconds. I'm going to square that. So this top value is going to be 64 feet squared per second squared divided by 2 times 32.2. That comes out to 64.4, but I'm going to round it down a little bit, and I'm going to call it 64, and I'm going to call it feet per second squared. And look what happens. The second squared cancels. Feet down here cancel. The square sign up here cancel. 64 divided by 64 is approximately equal to 1. And so our value is 1 foot. So our velocity head, in this case, is approximately equal to 1 foot. Now I know it's slightly greater than that, slightly less than that, because my denominator is slightly greater than 64, but I'm going to use that value as 1 foot. I'm going to use that in my little equation over here, and that's where that 1 foot comes from. So now I have all the values. Any questions before I erase this little these little handwritten formulas and stuff?
It's more of a statement. We have a guest from Colorado, and he is pointing out to be aware that if you're in projects in possibly Colorado or other parts where there's elevation of well over a mile or whatever, to take a look at that 33.9. It can be drastically less.
Yes, in fact, I was out in Colorado Springs several months ago, and we happened to be at a location that was 7,000 feet above sea level, and their atmospheric pressure was approximately 11.5, and if I multiply that by 2.31, comes out to 26.6 feet. And so instead of 33.9, it was 26.6. So yeah, you have to make sure. That's why I keep repeating that. In our case, we're at sea level. Sea level. As soon as you go to a different elevation, you have to change your atmospheric pressure that is associated with that elevation. And you can get that data. You can get it from the weather data. It's all kinds of fun stuff.
I bet you something like that could trick a person if they were taking a test someplace. You know what I mean? All of a sudden they didn't take into account, a test.
I bet you one of those questions is on the PE exam, don't you think?
Yeah, all of a sudden, this project's in at 6,000 feet, 7,000 feet. Oh, I got to change that number. Be careful. Yeah. Be careful out there.
Yeah. Okay, so let's just get rid of this, all these handwritten things here. So we've calculated, we simply did the arithmetic, we added and subtracted where appropriate, and we came up with 12.7 feet. And we said that our pump was 26 feet required, and the available is only 12.7. So guess what? Don't do that, because we've got a problem. Because the available pressure wants to be, in order to keep the pump from cavitating, above 26 feet, but it's below 26 feet. It's only 12.7 available. The pump is looking for 26. And so therefore we have a problem. And so then the next thing is, what can we do to solve the problem? So I'm going to give folks a few seconds out there, and they can type in and see what pops up, Brett. While you're doing that, I'm going to actually monitor the questions too. Let's see. Questions.
Anybody have some solutions for this
dilemma here?
Get a different pump, Thomas says. Raise the cooling tower, increase height, raise the cooling tower.
Yeah, so let's do it one step at a time.
Reduce the pressure drop.
Yes, so there it is. So we can go back to our equation. The first thing, let's take one more look here. Whoops, I didn't mean for that to happen. Let's go back here one more time and put in there's our pen. Remember, we cannot change the, once we've determined what the elevation is, let me just type, for some reason, oh, I know it. Let me just put those questions back for a second. Okay. So the atmospheric pressure is a function of elevation, so we have no control over that. So I'm going to kind of put, so we have no control. What is the problem here, Brett? Every time I touch the screen now with my pen, it wants to go to the next screen. So let's try this one more time. So we cannot change the atmospheric pressure. And since in this case, the cooling tower water that's going to the system is 100 degrees, that comes from the steam tables. So we cannot change that. So those two values are fixed in this particular example. So the only thing we can do is change the friction in the piping, the elevation of the cooling tower relative to the pump, the friction, and the velocity. Those are the only three things that we can control. We cannot control these two at the end. You can't control those. So yes, we had some people fill in some questions and they said, raise the cooling tower. Yes, if you can raise the cooling tower, you would increase the vertical distance. In our case, we'd have to raise to be above 26 feet. If we raise the tower an additional 20 feet, that would change this 12.7 into 32.7, and that would solve the problem. But that's pretty expensive to raise a cooling tower. The second thing is someone said, well, we could increase the pipe size to reduce the friction loss, or we can shrink the length of the pipe. Maybe we put the pump closer to the cooling tower. We could do that. And then the third thing is that we can, in terms of the formula itself, we can decrease the velocity. Remember, at 8 feet per second, I said that the velocity would be the velocity head would be approximately 1 foot. But in this case, it's not going to change by that much because my assumption is it's a relatively low velocity. And then someone also mentioned we could make a different pump selection, and that's a very possible solution here because a different pump selection would give us, instead of selecting a pump with an NPSH required of 26 feet, let's say, and I don't have any idea, by the way, if there's one out there, but let's say that the actual pump, instead of picking 26 feet, we could select one that had an NPSHR of 5 feet, in which case, if I subtracted 12.7, if I subtracted 5, from 12.7, I have 7.7. That's a reasonable margin of safety. Although I typically like to have a margin of safety of 10 feet. So whatever the pump requires, I want to have an available pressure that's at least 10 feet above what the pump requires.
We have another great answer or solution. Obviously, changing the HZ, right? By going up with the tower. What if you go down with the pump, right? You can actually lower the pump.
I mean, I've seen a couple of applications. I happen to be out in, the University of Central Florida. This was a couple of years ago, and they had their cooling tower sitting on grade, so they weren't elevated at all. But what they did was they built a big giant pit, and they put the pumps in the pit. It was really quite clever because the top of the pit had a metal grate on it, so you could walk over it. And since it was open metal grate, you could see down to the bottom of the pit. They had a floor drain at the bottom of the pit. There was a ladder and a hatch. You could open the hatch, you go down to service the pumps. And the pumps were approximately 15 feet below grade. So that's what they did for a solution. And they did a nice job. So yeah, you could put the pump down.
Here's some some interesting questions here. Where do you calculate the velocity head? At the pump inlet flange or the eye of the impeller? Great question,
At
Eric.
the pump inlet flange. So if the pump had an inlet size of, say, 4-inch, you would look up the flow, in this case 2,400 gallons per minute, and you would make sure that you pick the pump inlet size large enough to have an inlet velocity as close to 8 feet per second as possible. I mean, if you could get it for less than that, but we would definitely recommend that. But you can see what happens is that since it's a squared value, since the velocity pressure is equal to the velocity squared, if I double the velocity, went from 8 feet per second to 16, my pressure drop would go from 1 foot to 4 feet. It'd be 4 times greater for twice the velocity. So yeah, at the pump inlet flange.
And here's the question that always comes up in all of our presentations on NPSH, your presentations, we start with the open system. What about in a closed loop system? Do you still have to do the calcs? Obviously, the numbers are different, but it's still worrisome, I'm sure.
So the pressure in an open system is controlled by, in this particular example, which is the most common problem that we have out there, the pressure is controlled by the atmospheric pressure, which is a function of elevation. And once you pick the physical site for your design, you don't have any more control over the atmospheric pressure because it's a function of elevation. In a closed system, the open part of the system goes away, and that's replaced by the minimum pressure in the system, which is controlled by a combination of the fill valve and the expansion tank. So you, as the design professional, get to pick the pressure that starts the calculation. So instead of having the atmospheric pressure up here, I've got this little equation up here. Instead of the atmospheric pressure, it's the pressure or the minimum or fill pressure in the system. And you have control over that because you get to pick what you want for a pressure. So the question comes up in a closed loop pressurized system, do I have a cavitation issue? Well, you could if the pump, for example, was at the top of the building and it was a higher temperature system. So for example, if you had 200°F water, if that was open to the atmosphere at sea level, it wouldn't boil. However, if you had a pressure drop at the inlet side of the pump low enough, it could boil, in which case it would cavitate. So what are the red flags? The red flags are if you have in a closed loop pressurized system, if the pump is at the top of your column of water, which is where the lowest pressure is, and the water temperature is relatively high, in this case, a makeup one, say 200°F, it's possible to have an inlet pressure at the pump to drop to the point where the water will boil, in which case it will cavitate. So it can happen in closed loop pressurized systems if you have a relatively low pressure because the pump is perhaps in a mechanical penthouse at the top of the building and you have a relatively high temperature.
And so someone made a statement that 8 feet per second velocity seems a little high. Many systems have lower than that, and yes, that's true. But sometimes it's a little higher at the pump because of different things. But nonetheless, very true.
Yeah, so Brett makes an excellent point, and let me repeat what Brett said, is that when you make the actual pump selection, a lot of times the pipe is sized for less than 8 feet per second, but someone may select a pump that has 1 or 2 pipe sizes smaller than the actual, the pump suction flange rather, is 1 or 2 pipe sizes smaller than the actual pipe itself. And so you could have an unpredicted, I shouldn't say unpredicted, you could have a high velocity at the inlet of the pump if you don't take that into consideration. So that's an important little detail.
Here's a great question from Tony. Does the HZ number matter in a closed system?
Yes, the HZ is basically the elevation of the height of the column of fluid above the center line of the pump. So if you had the pump, for example, in the basement, and I know the pipe is never going to sit on the floor, but let's say it was in the basement, first floor, let's just use that. The first floor of a building, the building is 75 feet tall. The pressure at the inlet of the pump is a function of the column of the fluid. In this case, at 75 feet, that'd be approximately 32.5 pounds per square inch. So it does make a difference in terms of the static pressure in the system.
So Steve's asking if there's time, can he repeat the 3.75 cavitation segment? I don't remember that, Rich. Do you?
The 3.7, oh, no, I don't. Maybe he could elaborate while we answer a couple of other questions. I'm not sure.
I think more and more systems, cooling tower systems, we're starting to see issues because more and more projects, the tower is almost at grade. In the old days, I say the old days, the tower was up on the roof, right, of the building, 20, 30, 40 feet up and open to the atmosphere, but the pump was down in the mechanical room at ground level.
Yeah.
But more and more systems are not that way. So that's part of the reason that this is becoming more question.
Yeah, so let me just spit out a couple of very short, quick things. So when a pump is cavitating, sometimes people say it sounds like it's pumping rocks or marbles or ball bearings, whatever. And I put up a picture of what cavitation can do to an impeller. In this case, it completely destroyed the impeller. It probably would do that in a severely cavitating pump. It would only take a few weeks, and it would destroy the impeller. So cavitation has a huge impact on the life expectancy of the equipment, not to mention that if the pump is severely cavitating, it won't be able to maintain pressure and flow.
So he clarified the 3.75. I think this has to do with the HI testing, how we test stuff like that.
Okay, so the Hydraulic Institute requires that we have, if we get a degradation of 3%, and if you multiply 3 times the 125 PS, I'm sorry, the 125 feet for the differential pressure in the pump that we selected times 0.03, that's where the 3.75. So if your pressure degrades by 3.75 in that particular example, then the pump is officially cavitating in accordance with the Hydraulic Institute rules.
Rich, our friend Leah, and maybe you have somebody, but I know I don't. Do you have any colleagues that can discuss NPSH-RA on positive displacement pumps?
I do not.
Yeah, I
I
apologize.
don't
Well,
know. I don't know the geometry of a positive displacement pump or a gear pump. You'd have to go to the manufacturer, the folks that are experts that manufacture that equipment to help answer those questions. Sorry.
And Todd is asking whether this should be these numbers or the required or something. Should it be a scheduled items or who calculates it? You know, he says excluded because you're wondering if you feel NPSH-R should be scheduled for hydronic.
Well, again, every time someone does a pump selection, in my opinion, they should, in their schedule, show the net positive suction head required by the pump, and they should also have a separate column that shows the net positive suction head available in the system, and so that someone, it doesn't inadvertently pick a pump whose NPSH R value is greater than what's available. But if you put it in the schedule, you can't go wrong. It's in black and white, right?
Yeah, and my last comment, because we're getting close to, well, probably past a little bit, so that beautiful pump that you show there with the nice green color, that motor that's on top of it, because that's showing a little vertical pump. Many times the questions Rich and I get are for pumps with 200, 300, 400, 500 horsepower motors, not the ones with 2, 3, and 5 horsepower motors. So please, if you get involved in big systems, make sure someone on your team is aware of what we're talking about here.
Yeah, because like what Brett is hinting at, you know, if it's a 2 horsepower pump, it's not going to break the bank. But if it's a 500 horsepower pump, that's not chump change. That's a lot of money, big systems. I was just looking at a couple of NPSH issues in Florida a couple of weeks ago, and there were 250 horsepower pumps. So yeah, they get big.
We're all set for questions, Rich. Say goodbye.
That's it? No more questions out there?
No, we're losing. Thank you both, Andrew said. You're welcome, Andrew. A lot of thank yous. People are signing off.
All right. Thanks for joining us today. Take care, folks.
Everybody, we appreciate it. Again, 24 hours from now, the recording. Hopefully you downloaded the handouts. If you didn't, send us an email. I'll send it out to you. Not handouts, handout. It's a similar presentation to what you're seeing here. And I did have the schedule up. Oh God, I forgot what the heck it is. We have our next one coming up, but they are available. The next quarter Takeout Tuesdays are available on our website. They were put up earlier today. So if you want to register, feel free. And we will see you down the road. Great job, Rich, as usual. Take care, everybody. Goodbye.